Okay, so last time, so I have introduced you the determinant. So, and determinant was, well, the definition was not that hard because, well, it only had three properties: multilinear and alternating and unitary. And today I'm gonna show you so the explicit formula for computing the determinant. And to do that, today we will be working on a little thing on the group theory. Not terribly complicated, but which is considered very essential, especially when we are working in the determinant. So the first thing that I will introduce is the permutation group. So what is that? I have a set, so which I will name. So n sub n, not a good naming, but well, this is a subset of all integers. So this is very easy set. So it has just numbers, integers from 1 to n. Okay. And I'm going to define a permutation group Sn. So what is this? This is a collection of all bijective maps from this guy to itself. So do you know what I mean by bijection? Yeah, bijection is, well, so simply speaking, the bijective map is to be a bijective map, the bijective function actually builds a one-to-one correspondence between the target space and the domain space. So, and in this case, my target space and domain space, they are the same thing. So, well, every map has to be mapped to some other guy, and there is no two different arrows that comes to the same target. So the permutation group is just collection of bunch of functions, right? From nn to nn. The collection of all bijective functions from nn to nn. Okay, and well, and any typical element from in this group Sn is called the n permutation, or simply if there is no confusion, or then I will just say a permutation. Okay, so actually this is a finite set, right? Because we are talking about the functions between the finite sets. So Sn also must be, so there has to be finitely many bijective maps from nn to nn. Okay, so this is my quick question. So how many functions do you have for say S3? Yeah, so quiz. So what is so if I put these two vertical bars, for the set, for this finite set, that this implies that this means the number of elements of this set. So how many functions do you have in S3? I mean, in other words, how many bijections between three sets? Yeah, 6, which is 3 factorial, right? Great. Actually, I have prepared a small cartoonish picture for S3. So I have these 6 functions, and they consist of the S3. The first one is obviously the identity map, and the second one, which interchanges the first and second element, and this interchanges second and third, and this interchanges in first and third, and this is not exactly interchange, but well, this is still a bijection. So yeah, because of this reason, so you must have 6 different functions in S3. Okay. Well, so I say this is not a permutation set, but I say this is a permutation group. So this is a group because it has some sort of multiplicative structure in it. So in other words, you can pick up 2 different functions from Sn, and you can try to multiply them. I mean, this is not exactly multiplication, but that is actually a composition of two functions. Why? Because suppose that you have chosen two different bijective functions from Sn, and if you compose them together, then the resulting function is also going to be a bijection from Nn to Nn, right? So in this sense, the Sn has some sort of a multiplicative structure. Composition. Okay, and I say, so then there is some very important element in Sn. The most important one is obviously the identity map. And the next important object in Sn is so-called the transposition. So what are the transpositions? Okay. A n permutation from Sn. So this is a Greek letter, which should be read the tau. This tau is called a transposition. And transposition is a very special permutation. So which interchanges exactly two elements in Nn, and others unchanged. Okay. So in this picture, I think these three guys, they are the permutations. Okay, but this, and that, they are not the permutations. Okay, so in order to be permutations, so everything just carries over from domain to the target, but except for the two elements. So this is a transposition. And I want to claim that these transpositions is very special things, and these transpositions are actually the building blocks of the entire Sn. So what does it mean? So why they are the building blocks? Because every n permutation can be written as a composition of transpositions. Okay, so things are like this. So you can just pick any random element from Sn. Once you have chosen that Sn, once you have chosen that permutation, then I can make exactly the same permutation only by using compositions of the transpositions. This is possible for every n permutation. How do I prove this? Actually, the proof of this is not terribly complicated, but well, because I don't have enough time for this, so I will just leave. So I'm not just gonna prove this. So I will leave the proof as not as an example. I'm gonna, I will just omit it. But maybe I believe I can argue. Oh, sorry. Yeah. I can convince you by showing you a picture, showing you some example. This is a very easy exercise. This is very easy example. So I just came up with some random sigma, random permutation, 4 permutation. Then so 4 permutation. Oh, sorry, 4 permutation. So yeah, this looks quite random. So 1 goes to 3, 2 goes to 4, 3 to the 2, and 4 to 1. So this is clearly this is 4 permutation. And I will try to write this guy as a composition of transpositions. How? Just by doing this. So I have composed tau 1, tau 2, tau 3 in this order. Now, so let me keep track of these arrows. And if I compose these 3 transpositions, they obviously they are transpositions. Tau 1 exchanges 2 and 4, tau 2 exchanges 2 and 3, and tau 3 exchanges 1 and 3. So tau 1, tau 2, tau 3, they are all transpositions, right? And 1 goes to 1, and 1 goes to 1, and 1 goes to 3. So 1 goes to 3, right? And 2 goes to 4, 4 goes to 4, and 4 goes to 4. So 2 eventually 2 goes to 4, and 3 to the 3, 3 to the 2, and 2 to the 2. So 3 goes to 2, and 4 to the 2, 2 to the 3, and 3 to the 1. So 4 to the 1. Okay. So so in this way, so I can say sigma is the same as the composition of tau 3 of tau 2 of tau 1 in this order. Okay. So so this is possible. So writing down any permutation as a compositions of transpositions, which I will from now on, which I will say a transposition decomposition. All right. Such a decomposition is not unique. So what does it mean? So for any given n permutation sigma, I try to decompose it into these very special transpositions, compositions of these very special transpositions. But however, if you can spend enough time and effort in transposition decomposition of the same sigma, then you can actually find out completely different set of transpositions which compose into the exactly same permutation. Okay. So in this way, such a decomposition is not unique. So for instance, here I have decomposed sigma as a permutation sigma as a decomposition as the composition of tau 3, tau 2, and tau 1. But at the same time, I can show you a different transposition decomposition of the same sigma. Like, yeah, I know this sounds very silly. So what about this? Yeah, actually, okay. It is very easy to see that if you compose two the same transpositions, then it's going to be identity, right? So, however, this is a transposition decomposition, and this is another transposition decomposition, and they are different. So I just want to emphasize that transposition decomposition is not unique. Okay. So what is the big deal? So why do you even care about this transposition decomposition? So this is a theorem, and the theorem says for any given n permutation sigma, and suppose that I was able to obtain two different transposition decompositions of the same n permutation sigma. Okay. Let us assume this. And so they are the transposition decompositions of the sigma. And I claim that 2 divides k minus L. Oh, hold on, what is k and what is L? K is the number of the transpositions that appears in this decomposition, and L is the number of transpositions that appears in, yeah. Oh, sorry, so I have to mention, so tau I and lambda j, they are all transpositions. Sorry, I have to mention this. And so L is the number of transpositions that appears in this transposition decomposition. Okay. And K divides, 2 divides K minus L implies the parity of two integers K and L must be the same. So do you know what I mean by parity? The even and or odd. So in other words, suppose that I was able to decompose sigma by odd number of transpositions. Then if K is an odd integer, then this implies L also has to be the odd integer, right? And on the other hand, so if I was able to decompose a sigma into even number of transpositions, then this L also must be even. So in this sense, I say the parities of K and L must be the same. Okay, so this is the meaning of the theorem. All right, how do I prove this? Actually, I don't approve this. Sorry. So well, frankly, so honestly, so in last years I proved the state theorem and I proved the theorem by like spending 1 hour. So it takes a lot of time and effort, but I don't believe that was quite nice approach because yeah, at the time of the year, so most of my students they just fell asleep. So I'm sorry. So just take this for granted. So if you're interested in this kind of statement, then why don't you go to the abstract group theory in next semester? Yeah. Well, just trust me. Yeah. This is very commonly known fact in the elementary group theory. So however, if you're interested in the proof of the theorem, so why don't just email me? Then I'm gonna send you the lecture note from my lecture note from my previous year. Okay, so let me just take for granted. So far we have learned any n permutation allows a transposition decompositions, and although the transposition decomposition is not unique, but the number of the transpositions that appears in that transposition decomposition. Sorry, I messed up. Sorry. Let me try one more time. But the parity of the number of transpositions that appears in the transposition decomposition is always well defined. Right? Yeah. Yeah, it's kind of getting confusing. So let me repeat one more time. The parity of the number of transpositions that appears in the transposition decomposition is well defined. Okay, all right. Okay, so now I want to define the sign of a transposition, so sign of a permutation. I have a permutation group Sn, and I just picked up some random element sigma from Sn, and well, suppose that sigma can be written as a composition of k transpositions. Okay, this integer k is not unique, but the parity of this integer k is always unique, well defined, right? So I want to define the sign of called a number, sign of sigma, which is always plus or minus 1, and defined like this: -1 raised to the power of k. Well, in this, if I define like this, then even though k is not well defined, but this number is always well defined. Okay. So if sine of sigma is +1, then we say sigma is an even permutation. And if sine of sigma is -1, then we say sigma is an odd permutation. Yeah, I quite like this naming because we say this is an even permutation because, well, it consists of even number of transpositions. And if sigma is an odd permutation, then with that imply that sigma has odd number of transpositions in their transposition decompositions. Okay. Okay, all right. Okay, I believe you must be wondering, so why I just turned into this group theory? And this group theory is very much related in computation of the determinant. So we can associate any n permutation sigma to an n by n permutation matrix which I will say P of sigma. And this matrix is defined like this. E of sigma 1 and two E of sigma n. I believe you remember this notation. This notation means the standard unit vectors. And sigma of 1. So this is, well, sigma of 1 must be a number between 1 to n. This must be some number. Yeah, you know, the sigma is a function. So if you plug in this function, if you plug in 1 into this function, then the output of this function must be some number between 1 to n, right? So in this way, I can associate an n by n permutation matrix with this n permutation. All right, so a small quiz. Suppose that I have chosen the identity element from Sn. Identity is always the member of the Sn, right? And what is P of the identity? Identity matrix, right? N by n identity matrix. But usually P of sigma is not an identity because, well, so you know, so this permutation matrix, every row of this permutation matrix was obtained by shuffling the rows of the identity matrix. Okay, right. Again, this is very important observation. Can you guess the determinant of this matrix? I guess the determinant of this matrix must be precisely the same as the sign of the sigma. Why? Do you get it? You must remember that determinant is alternating, and determinant of the identity is 1, always 1, because the determinant was unitary. And whenever you exchange two rows, then your determinant must change the sign. And you know, P of sigma was obtained from the identity and shuffling the rows, exchanging the rows. Then how many row exchange appears for P sigma? exactly the number of transpositions, the number of transposition that appears in the transposition decompositions of sigma, right? Because of this reason, determinant of sigma must be the sign of this permutation. Once you have agreed on this fact, then you're almost done. You're like 50% done for today's lecture. Great. Okay. Now what? So I will just go back to all the way to the. So last time, so I tried to compute the determinant of the 3x3 matrix. And it turned out I ended up with an expression that consists of, sorry, I messed up. I should not be speaking and writing at the same time. Yeah, okay, great. And last time I tried to compute the determinant of 3x3 matrix. And I somehow ended up with an expression that has six terms. See, I have 6 terms. And so, well, and last time, so we struggled to compute the determinant of each of these 3x3 matrices. And I guess this is precisely these are precisely the matrices which can be associated to these 3 permutations, right? Okay, so and the determinant of each of these matrices is precisely sigma of this permutation, right? So this number was sigma of the identity, and this number was sigma of a transposition which exchanges number 2 and 3, and this is a sigma of transposition that exchanges the first and second, and so on, right? Okay, so maybe I can write this entire expression into this compact form. So A1 sigma of 1, A2 sigma of 2, A3 sigma of 3 times determinant of P sigma. Yeah. Well, you must be wondering, so why I'm writing this. So okay, let me go back to this. Let me go back to each of these factors. So A11, so every subscript is 1, 1, 2, 2, 2, 3, and 1, 2, 3, 3, 2, 1, 2, 2, 1, 3, 3. So can you read the pattern? So the second subscript is exactly the image of the first subscript under this sigma, right? So 1, 1, 2. So you know the permutation which can be associated with this matrix was a permutation which interchanges 2 and 3, right? So 2, 3, and 2, 3, 2. And the permutation that can be associated with this matrix was interchanging the first and second. So 1, 2, 2, 1, and 3, 3. Right? Can you see the pattern here? So, well, summarizing this, I can say A of 1 and sigma 1, 2 and sigma 2, and 3 and sigma 3, and followed by the determinant of P sigma. Okay, so far so good? Okay, all right. But this is just, I would just say sine of sigma times this. Please allow me to write this, right like this. So this is the formula that appeared, which was given in our textbook. Okay, all right. Okay, now I really want to generalize this. So since we arrived the formula for the determinant for the 3x3 matrix, but this trick can be easily applied to higher, so like larger matrices. So in general, if A is an n by n matrix, then I hope you agree on this statement. A 1 1, A 1 2, A 1 n, A 2 1, 2 2, 2 n, A n 1, n 2, da da da, A n n is summation of all permutations in n permutation group times of sine of this permutation times A1 sigma 1, A2 sigma 2, A n sigma of n. I believe this is the right formula for computation of the n by n matrix. Right? Okay. Yeah, I really like it. So okay, so so we actually derived very nice looking formula for computation with determinant. But I believe no one is using this formula in actual computation of the determinant. Why? Because it has too many terms. So it chooses sigma from the nth permutation group Sn. And what is the size of the Sn? Size of Sn is precisely n factorial. N factorial, which is very large number. Suppose that you try to compute the determinant of 10 by 10 matrices, 10 by 10 matrix. Then there must be 10 factorial many terms appears in the summation, which is not that great. So, this formula looks very beautiful and very elegant. Yeah, I agree on that. But so we will need actually better formula than this. So, actually, so when they try to compute the determinant, then they use a very nice technique, which is called the cofactor expansion. So which I will introduce from now on. And in order to explain the cofactor expansion, then I will also need to explain the notion of the inversion. Okay. Okay, sorry. Let suppose I have sigma, and from now on, we will sometimes write to describe a permutation. So, well, as of now, so far, so in order to describe any permutation, then I draw the map. So I draw the cartoonist picture, 2 columns and arrows between them, and which is not very systematical way to expressing a permutation. So from time to time, we will write sigma 1, sigma 2, and sigma of n. Okay. So before we move on, so let me practice a little. Suppose I have a 1, 2, 3. Two, 1. So let us practice a little. Well, this is a 3 permutation, and let me describe this permutation using this notation. Do you think you can do this? Okay, let me try this. 1 goes to 3. So therefore, the first number appears here. It's going to be 3. And 2 goes to 1. So the second number must be 1. And 3 goes to 2. So the last number must be sorry. 2. Okay. So this is an easy notation. Yeah. And if we use this notation, then we can define very interesting number for this permutation. So which is called an inversion. I have a n permutation sigma here. So J1, J2, Jn. And these integers from J1 to Jn, they must be the integers from 1 to n, right? And suppose that I was able to find 2 integers, s and t, 2 distinct integers. And let me say s is less than or equals to t, less than t, such that, I messed up. Sorry. Js is greater than jt. Then this pair, we say this is an inversion of sigma. And then the number of such pair is called an inversion number of sigma. Okay, so basically, what is an inversion? So inversion, so for any given permutation here, and if you can find a pair of numbers, so which is not respecting the natural order of the integer, then you can consider that pair of number as an inversion. And inversion number is counting such number of pairs. So again, let us practice this. What do you think is the inversion number of this permutation? I can see I have 3 and 1 here, and which is actually the opposite of the natural order of the integers. So there I can find 1 inversion, and 3 and 2. Yeah, 3 came before 2, and this is an opposite of the order. So there's another inversion. But here I have 1 and 2, but this is 1 appears before 2, and so this is not an inversion. So therefore, the inversion number of this inversion number of this permutation is 2. Okay. One, 2, and there was 1 inversion here, and another inversion there. So, so inversion number is 2. Okay. Let me try just one more exercise. This is 4, 6, 2, 5, 1, and 3. I have 6 integers, so clearly this permutation belongs to S6. So how many inversions can you find? Let me try. 4 and 6. This is not an inversion, but 4, 2, this is an inversion. And 4, 5, not an inversion, but 4, 1, this is an inversion. And 4, 3, this is an inversion. So I found 3 inversions starting from 4 and 6. How many inversions? Yeah, I have many inversions. This is an inversion. Another inversion. Basically, everything is an inversion. So I found 4 inversions here. And from 2 to 5, this is the inversion. But 2, 1, this is an inversion, right? So I found another inversion from 2 to 1. And 2, 3, this is not an inversion. And 5, 1 is an inversion. And 5, 3 is another inversion. And that's it. And there is no inversions starting from 1 and 3, right? So I have this many inversions. So how many inversions do I have? So in conclusion, 1, 3, and I have 3 red curves, and 1, 2, 3, 4 blue curves, and 1 green curve, and 2 light green curves, and so 3, 4, 7, 10. So this is the inversion number of the permutation. Okay. Okay, great. I guess so. As of now, I guess you have somehow understood the notion of the inversion number. So inversion number is very well-defined number for any permutation. Now, there is a very strong relationship between the inversion number and the sign of the permutation. this is a theorem. For any n permutation sigma, the sign of the permutations of sigma is the same as -1 to the power of the inversion number of sigma. Okay. Okay. So I will do my best to justify the statement. So to prove this, yeah, I had to come up with another silly notation called the adjacent transpositions. So what is the adjacent transposition? A permutation sigma, a permutation alpha is called a adjacent transpositions if alpha is a transposition and it exchanges two adjacent integers, I and I plus 1. So such a transposition is called the adjacent transposition. Okay, and there is a very interesting observation. For any n permutation sigma and any adjacent transposition alpha, and if you compose alpha and sigma together, alpha of sigma, then the inversion number of this guy, this is a permutation, right? Inversion number of this permutation is always one more or one less than the inversion number of sigma. Right? Agreed? Why? Because, well, suppose that this guy has been composed by adjacent transposition of 1 and 2. Then that only exchanges this number and that number. So exchanging these two adjacent integers almost has no effect on the inversion number. But for this, except for this green curve right here. So if I exchange number 1 and number 2, then this inversion just appears, right? This inversion disappears. So because of this reason, if you compose any permutation with adjacent transpositions, then the number of inversions just changes by 1, plus or minus, but always changes by 1. Yeah, that is the point. Now, and this is another very interesting observation. Every transposition can be written as a composition of adjacent transpositions. Transposition is a permutation, and every transposition can be written as a composition of adjacent transpositions. So precisely, suppose that I have a transposition that exchanges integer I and integer I plus d. Then it requires exactly 2d minus 1 adjacent transpositions. So, well, if you compose 2d minus 1 adjacent transpositions, then you can make this transposition. Okay. Right. So why is it true? Because this argument, I can prove this by using the induction. So I'll try to prove by induction. So suppose that D is 1. And so if I have transpositions that exchanges I and I plus 1, then this is already an adjacent transpositions. So therefore, I will need exactly 1 adjacent transpositions to achieve these transpositions. So this is clear. Okay. So if D equals to 1, then this claim is true. And suppose that if my transposition tau exchanges I and I plus D. So which is this, right? But I can decompose these transpositions like this. This transposition like this. I exchange 1 and I plus 1, followed by transposition that exchanges I plus 1 and D plus 1, I plus D. And again, followed by another adjacent transpositions exchanging I and I plus 1. Right? So I goes, and if you compose this all together, I goes to I plus 1, I plus 1 goes to I plus D, and I plus D goes to I plus D. Okay, and this guy goes to here and goes to here and goes to there. So I plus 1 goes to I plus 1, and I plus D goes to I plus D. It goes to I plus 1 and goes to I. So composing this is the same as this one. But can you see this? So in this side of the composition, I have two adjacent transpositions. And between them, I have a transposition which interchanges I plus 1 and I plus D. Right? Now, according to the induction hypothesis, I will need precisely 2D minus 3 many adjacent transpositions to achieve this, right? And combine with two additional adjacent transpositions between them, then I will need precisely 2D minus 1 adjacent transpositions. Okay? So I say you apply the induction hypothesis here. Induction hypothesis here. So we need 2D minus 3 adjacent transpositions for this transposition. Plus, I have two other adjacent transpositions. So therefore, in summary, I need 2D minus 1 adjacent transpositions to achieve these transpositions. So therefore, the claim has been proved. Okay. Okay. Wow. So so therefore, suppose that my permutation has this looking transposition decompositions. So each of these taus, they are transpositions, but they may not be adjacent transpositions. They are just regular transpositions. But every transposition now allows the adjacent, well, decomposition consisting of the adjacent transpositions like this. So I can do like that, right? And I put one additional identity over here. Then what is the sign of this signature? So what is the sign of this permutation, right? Sign, well, these adjacent transpositions, they are still transpositions. So therefore, sign of this permutation must be minus 1 raised to the power of 2D minus 1 plus 2D 2 minus 1, all the way up to 2DR minus 1, right? And, but, you know, whenever you apply the adjacent transpositions, then inversion number raises or decreases just exactly precisely by 1, right? So therefore, this number, the parity of this number must be the same as the parity of the inversion number of sigma. Okay, so claim has improved. Great. Okay. Okay, we are not out of wood yet. So we still have lots of things to do for today's lecture. Now I'm gonna do something very crazy for this. Okay, I have a permutation. This is, yeah, I have 5 integers, so this is 5 permutation. And describing this permutation using this picture, so I may have this picture describing this. So 1 goes to 3, and 2 goes to 4, 3 goes to 2, and 4 goes to 5, and so on, right? And for some crazy reason, I really want to get rid of the number 1 from the domain. then deleting number 1 from the domain will automatically cause deleting 3 from the codomain target space. So this is what I got. This is something that I get as a result. And I will try even crazier. Oh. So now this resulting picture only has 4 numbers in the domain and 4 numbers in the target. And then what I want to do is very simple. So since my number is starting from 2 to ending at 5, but I want to make this one something more looks like a 4 permutation, not 5 permutation. To do that, I'm gonna decrease each of these integers by 1. So 2 is now 1, and 3 is now 2, and 4 is now 3, and like this. And 1 and 2 they just carry over. But since I do not have 3, so these numbers must be decreased by 1. So just in order to more look like the permutation in S4. So I like this. So just the name changes, but nothing actually changed. Nothing essential has been changed. But just by doing that, now this one more looks like a 4 permutation. Okay. So 1 goes to 3, 2 goes to 2, 3 goes to 4, and 4 goes to 1. Now, why am I doing this? And this is something to do with the inversion number. So on the other hand, I want to compute the inversion number of this permutation. And how many inversions do I have? 1 inversion and another inversion, and this is 1 inversion and another inversion here, and I have another inversion there, and another inversion right here. Okay. So total inversion number, which is I have 2 inversions over here, and 1, 2, 3, 4. I have 4 another inversions right there. So total inversion number must be 6. And I intentionally decompose this number into 2 plus 4, and this number 2 actually came from this number, right? So this number came from because sigma of 1 was 3, right? Sigma of 1 was 3, so therefore there must be 2 numbers behind them. So the sigma number 1 is 3, so there must be 2 numbers, which is 1 and 2, less than 3, that came after 3, right? So this is why I get 2, and this number 4 came from these 4 numbers, 4, 2, 5, 1. Okay. So this number actually came from the 4, 2, 5, 1. Yeah, this is not formal. This is not official notation. So I just got this just because I'm writing this just in order to emphasize. I just got rid of number 3 here. And the inversion number from here is the same as inversion number of this. Okay. Okay. So now we know the sign of permutation is the same as the sign of the number of the -1 raised to the number of the inversion. So sign of sigma is going to be so this guy, this sigma tilde, which will be representing this one, this 4th permutation, times sine of sigma tilde. Okay, why? Because sine is the number of the number of inversion that you can find here is the same as the number of this inversion, and I have two inversions on the top, so minus 1 to the square times sine of sine of sigma tilde. Okay, all right. So in general, if sigma is a permutation, that maps 1 to j. If sigma is a permutation which maps 1 to j, then the sine of sigma is gonna be minus 1 to the j minus first times sine of sigma tilde, where sigma tilde is a n minus 1 permutation such that and sigma I plus 1 minus 1 if sigma I plus 1 is greater than j. So this sigma tilde is not a big deal. So sigma tilde is obtained, well, this sigma tilde is obtained exactly by getting rid of the arrow starting from 1 to j. So sigma tilde of I is okay. Oh yeah, okay, great. One is less than j. I plus 1. Okay, good. Yeah, great. Okay. So I'm doing the same thing. So here I put minus 1 to the j minus first. This is because if 1 maps to the j, then the first letter that appears in this sigma this permutation must be j, right? If one is maps to j, then the first letter must be j, right? Then there must be j minus 1 element after appearing after that, which is less than j. J minus 1 integers appearing behind of the first integer. So therefore, you must have n many such arrows starting from the first one to this. So sorry, you have precisely j minus 1 such arrows starting from to here and there, right? So therefore, this number represent these arrows. Okay. Okay. All right. Okay. Great. The cofactor expansion. So Okay, so now we came back to the determinant. So this is our determinant. So this is the determinant formula for n by n matrix. I have n factorial many such permutations in Sn, but I want to classify each of these permutations depending on the image of 1. So sigma of 1 goes to j. Yeah, here, so this set consists of many different permutations, but some permutations sends 1 to 1, but some permutation sends 1 to 2, and some permutation sends 1 to j. And we are classifying each of these permutation by depending on the image of 1. Okay. Then this one can be written as 1j. Okay. Right? Okay. And now this sign is, now I am replacing the sign of sigma by sign of this. I minus 1, j minus 1 times sign of sigma tilde. And so I'm gonna move minus 1 to the j minus 1 and a1j out of this parenthesis. Okay. I want to focus on this factor. For me, this factor again looks like some determinant. So, okay, actually, this number represents determinant of some matrix, but what matrix? I'm going to explain from now on. Given n by n matrix A, we define an n minus 1 by n minus 1 matrix, which I will call Mij. Obtained by deleting i's row and j's column of A. So for instance, if I have this matrix, then what is M12? M1 to be a 2 by 2 matrix, which is obtained by deleting the first row and the second column. So it must be A 2, 1, 3, 1, 2, 3, A 3, 3. Okay. Okay. Why am I introducing this matrix, this notion? Because for me, this is precisely, well, so whenever you look at these numbers, so the index A, so there are two indices bottom of each of these numbers, and this the first index never be 1. It always starting from 2, and the second index, which is the column, which represents the column index, but this second index can never be J, right? Because since we are talking about the permutation, right? So if J1 was, if I sigma of 1 was J, then there can be no J's for these indices, right? Because this is sigma is a permutation. So that means in this second index, you can never be able to find J here, right? So I believe this is precisely the determinant of M1J. Okay, so determinant of A is, oh, sorry. This is determinant of M1J. So from J1 to N minus 1, J minus 1 times A1J times determinant of M1J. So in order to make my notation more compact, so this is a notion of, this is called the cofactor. So given n by matrix A, Cij is defined to be minus 1 to the j minus I times determinant of the n minus 1 by n minus matrix and ij. So, but you know, the parity of j minus I is always the same as the parity of I plus j. Okay, and this number is called the cofactor. This number is called the ij cofactor of A. So summarizing this, now we are at the conclusion of today's lecture. Cofactor expansion. So if A is an n by n matrix, then determinant of A is, which is this, but A ij times ij cofactor Cij. This is the cofactor expansion. Okay. Yeah. Sorry, I know I just ran out of time, but just give me. Will you please give me just one more minute? Yeah. Thank you. Let me try to compute the determinant of this guy. So since we are using the cofactor expansion, so the first number in cofactor expansion, so this number times cofactor of this, so which is the determinant of this guy times -1 to the 1. This is 1 and 1 component. So this is 2 times determinant of this guy and plus -1 times, and this is 1, 2 component of this entry. So 1 plus 2 goes over here, and -1, 0, 0, -1, 2, -1, 0, -1, 2. Okay. So because I just got rid of these two, so this matrix must be here. So you are supposed to compute the determinant of this guy. You can, well, at this point, you can just try to compute the determinant of the 3 by 3 matrix because you know how to compute the determinant of 3 by 3 matrix. But if you don't, and also, yeah, sure. So also I have the 0 times another cofactor, but 0 doesn't count. So you can simply ignore this in this case. And you can choose to compute this determinant, or you can apply the cofactor expansion just one more time to compute the determinant of this guy. Okay. Right. So this is the cofactor expansion. All right. So this is for today, and see you next time. Thank you.